Now we move to the third topic of this lecture series, which is about thermodynamics and normal mode calculation. I have put these two topics together because normal mode calculation and the associated thermodynamics, they are both coming from frequency calculations or vibrational spectrum calculation. So this topic will be a bit lengthy here. So the first question is, what are the normal modes? When you talk about normal modes, you're actually talking about vibrational motion of atoms. So the collective vibrational motions of atoms, they are called as normal mode analysis. So these are probed in IR and Raman experiments, and you can have 3n-6 modes for nonlinear molecule and 3n-5 if the molecule is linear. So for example, if you talk about water molecule, you can have these three normal modes possible: bending, symmetric stretching, where both OH bonds are stretched out, compressed in symmetrically, or asymmetric stretching, where one OH bond is stretched whereas other OH bond is compressed. The potential energy surface is approximately harmonic at stationary point. You can see here it is approximately harmonic in this region close to the stationary point, and it becomes anharmonic at the sides. For example, if you move away from the stationary point or a minimum, then the potential energy surface start becoming anharmonic. For example, the pink color is harmonic model, whereas the blue one is anharmonic. So now you can see here, the pink one is perfectly harmonic. The blue one is anharmonic because the right-hand side is different than the left-hand side. And now you can see here in this region here, both blue and purple, they are almost like behaving as harmonic. So that's why the normal mode analysis or vibrational spectrum calculation, they are generally based on harmonic approximation. And we know that to calculate vibrational frequencies, we have this classical equation 1/2 pi c k over mu square root, where k is the force constant and mu is the reduced mass. K, the force constant, which is actually coming from the second derivative of energy with respect to coordinates. And this is what we have seen previously when we talk about Hessian. The Hessian is actually second derivative, and that second derivative gives information about the force constant. Mu is the reduced mass of the mode, which can be calculated from the masses of the atoms involved. And c is the speed of light. So normal mode calculation is actually coming from Hessian. So normal modes are eigenvectors of Hessian, and force constants are the eigenvalue. In this case, the normal modes are eigenvector of Hessian, and the force constant are the eigenvalues. And to solve this Hessian matrix, we take the approach of diagonalization, where a square matrix can be broken down into the products of three square matrices. For example, if you talk about matrix A, it can be broken down to P, D, P inverse, where P is a square matrix, and the columns here are eigenvectors. I mean, they are telling us about the normal modes. And D is a diagonal matrix, where the diagonal elements are eigenvalues. I will show you on the next slide how these diagonal values are useful to us. So for normal mode, this H Hessian is broken down into P, K, and P inverse. P here is another square matrix. This K is also a square matrix. Now, in this case, only the diagonal values are non-zero. Only the diagonal values are non-zero, whereas all other non-diagonal values are zero. These diagonal values are actually the force constants for vibrations, or sorry, force constant for normal modes. Now in this case, P matrix here, these columns are nuclear displacements associated with normal mode. Now you can see here it contains two numbers. The first index, the one here, 1, 1, and 1, so on. The first index indicates direction, like in which direction the atoms will move. The second digit here indicates the mode. Now when we talk about the modes, in this Hessian we include not only the vibration but also the translation and rotation. So 1 to 6, like these 1, 2, 3, 4, 5, 6, these 1 to 6 are translations and rotations, whereas 7 to 3n are vibrations. Now in the case of K, which is diagonal matrix, only diagonal elements are force constant K. K1 to K6, they represent translation and rotation, whereas K7 up to K3n are vibrations. So mass swing gives the vibrational frequencies, as you can see here. So now you can see here, a complex Hessian matrix is broken down into two useful matrices, which are P, which gives us information about the direction as well as the mode, whereas the diagonal elements in this K matrix, they tell us about the force constant associated with these normal modes. 1 to 6 are translational and rotational modes. 1, 2, 3 are translation. 4, 5, 6 are rotation. And from 7 up to 3n, they are vibrations. So P and K are useful for characterizing stationary points, visualizing normal modes, calculating zero-point vibrational energies. We'll see this in a bit here. They are useful in simulating IR and Raman spectrum, which will come in a future lecture, and finite temperature correction, which is also going to come in a later lecture. So going back to characterizing stationary point, if you talk about a minimum, the second derivative should always be positive. It means that there should be all positive values for all Qi. It means the K or the force constant are positive. So all positive elements in Hessian mean all diagonal elements of K are positive. If K is positive, then the frequency is positive. So it means the minima are characterized as having all positive frequencies. For transition state, we mentioned earlier that we have exactly one negative value or less than zero value. One value for the second derivative is less than zero for exactly one Qi, and that Qi is the direction of reaction coordinate, where reactants are going to products. So one negative element in Hessian means one diagonal element of K is negative. And if K is negative, the frequency is negative, which is also called as imaginary frequency. So whenever you read somewhere in the literature that a frequency is an imaginary, it means that imaginary frequency is a negative number. And that is a characteristic of a transition state. Transition states are characterized as having exactly one imaginary frequency. So if you see no imaginary frequency, that's not a transition state, that is a minimum. If you see more than one imaginary frequency, that is not the right transition state. I mean, you need to relocate that transition state with one imaginary frequency because it should be exactly one. Now, we have seen that how to characterize a transition state. One way is to look at the second derivative. It might be possible that you optimize a structure, you run frequency calculation, you get one imaginary frequency, but still it does not confirm you that you got the right transition state. There must be some other ways that can help you in deciding whether you got the right transition state or not. So I'm going to show here a few methods which can help you in deciding whether you got the right transition state or not. The first one is to look at the structure. Does it look right? Because that is not very much absolute method, but that is going to give you somewhat good idea of the structure that you are aiming and the structure that you have got. If you got the structure that you are expecting, that can give you an idea that probably you got the right transition state. It's a pretty weak confirmation method, but it helps sometimes. That's the first way. Then look at the structure. If it looks right, or it looks fine to what you are looking for, or you anticipating, it means you got probably the right transition state. And the second part is, or the second method is to look at the energy of the transition state. It must be higher than the reactant end product. If you happen to get a structure here, which is higher energy than reactant end product, more likely you got a transition state. But again, it is not very much confirmatory method, because having high energy does not mean that you got the right transition state. It simply tells you that you got a structure which is higher energy than reactant end products. But these two are very common, simple methods, but they are not very much confirmatory. Look at the structure. Does it look fine or not? Then second one is to look at the energy, whether the energy of the transition state is higher than the reactant or products. Generally, the energy of the transition state is higher than reactant and products, provided that both bond breakage and bond making is involved. But if you happen to only break a bond or to make a bond only, then the energy of the transition state lies between reactants and products. The third one is to animate the normal mode with the imaginary frequency. You will get one imaginary frequency, the first one, and you will have to animate it to see what type of motion does it correspond to. So the normal mode with the imaginary frequency correspond to the motion of the molecules over the energy barrier. Does this motion connect the reactants to the product that you have in your mind? If it connects to the structures of reactants and products for your reaction, then you got the right transition state. So animation of the normal mode is a better approach as compared to looking at the structure or the energy of the transition state. But the surefire to confirm a transition state is to perform IRC calculation, intrinsic reaction coordinate. Now in IRC calculation, you start from the structure of the transition state and you follow the lowest energy trajectory or pathway in each direction along the imaginary normal mode. Now, do these pathways lead to the reactants and product? That is very much confirmatory to the transition state. Let's say what happened in IRC, you start from this structure and you allow the system to relax on either side. And if you happen to get the same structures of reactants and products that you have for your reaction, then definitely it means the structure of the transition state is the right one. But if you happen to get some other reactants or products than what you have in your mind or in your hand, then probably you got the wrong transition state. IRC calculations are expensive and rarely necessary, but they are a surefire way to characterize the transition state. As I mentioned that the energy of transition state should be higher than the energy of reactants and products, provided that both bond making and bond breaking are involved. So energies can be calculated relative to reactants. If you talk about energy of reaction, it is energy of product minus reactant, whereas the energy of activation is the energy of transition state minus energy of reactant. And to calculate or to make this reaction profile, you set the lowest energy structure as 0. Set reactant energy to 0, and all energies must be calculated at the same level of theory. What is the level of theory? It will be discussed in a later lecture.